Okay, so this is a continuation of our lecture on probability. We already talked about basic probability and counting number of ways that some event can happen and the total number of things that can happen. And we use that for some simple probabilities and some more tricky probabilities. I also showed how to do simulation to come up with a probability using relative frequency. And we also talked about one of the main counting techniques, which is using permutations or combinations to figure out the number of ways that something can happen. The number of permutations of taking 5 letters 2 at a time. And this was the number of combinations of taking 5 letters 2 at a time. So we had formulas for combinations and permutations, but those functions are all built into the calculator. And we talked briefly about how the combination numbers show up on Pascal's triangle. So now let's talk about a couple other types of probability, conditional and marginal probability. So this is some data from the Titanic, and this is focusing only on adult male passengers. So not getting females or children into the mix, just looking at adult male passengers. And this type of layout is referred to as a two-way table because it's showing the distribution of 2 different variables. In this case, we're talking about what class the passenger is and their mortality, whether or not they survive. If we just look at one variable at a time and we focus on either the row totals or the column totals, we have a marginal distribution. So for example, the marginal distribution of class is that first class has 176 passengers, second class has 167, third class has 452, total of 795. Or you can look at that distribution in terms of proportion, which is better for our chapter on probability. So in first class, there's 176 out of 795, which is 22%. And in second class, there's 167 out of 795, which is 21%, and so on. So that's the marginal distribution of class, looking at the numbers in this margin here. You could also have the marginal distribution of mortality if you look at these numbers here. 664 out of 795 died, which is 83%. 131 out of 795 survived, which is 16%. So those are marginal distributions or marginal probabilities. So if you picked an adult male passenger at random, the probability that they survived would be 131 out of 795. There's 795 names that could be chosen, and 131 of them belong to survivors. So the probability that someone survived is 131 out of 795. Or you could say, what's the probability of first class? And those are called marginal probabilities, just looking at one value of one variable. It's more interesting, however, to look at the distribution of each variable given a particular value of the other variable. Now, this is a lot more writing, but it's much more interesting, and this helps us determine or investigate relationships between variables, and such a distribution is referred to as a conditional distribution. A conditional distribution of class among those who died. So I'm going to go split screen for a second so you can see the table along with the notes. So there's the table. So conditional distribution of class among those who died. So now I'm focusing on this column here, only looking at the column of people who died. Among those who died, the distribution of class. So 118 of the 664 that died are first class, which was 17%. And 154 of the 664 that died were second class, 23%, and so on. So when we were looking at the numbers over here, that was the marginal distribution. Now I'm only focusing on the distribution of class among those who died. That's a conditional distribution. And then we can also look at this column and get the distribution of class among those who survived. So that would be this section here, the distribution of class among those who survived. So for example, of the survivors, 58 out of 131 of them were in first class. So 44% of the survivors were in first class. And because this distribution of class is different for the different values of mortality, so among those who died, 17 were first class, but among those who survived, 44 were first class. Because these distributions of class are different for the two different values of mortality, that suggests that there's a relationship between class and mortality, or you could say that someone's class depends on whether or not they survive, depends on their mortality. As a probability, this is also called a conditional probability. And the common notation is the probability of, and then in parentheses, A vertical bar B. And the vertical bar is usually taken to represent the word given. So the probability of A given B, or the probability that event A happens given that event B has happened, or sometimes old school is to say the probability that A happens conditioned on event B happening. So for example, in our example, the probability of first class given that someone survived. So let me go back up here. Among those who survived, the probability of first class is 44.27. So the probability that someone is in first class, given that they survived, is 4427. Another way of looking at that is, let me move this split up just a little bit. Another way of looking at that is that given that someone survived, we're only talking about 131 people. And of those 131 people, 58 were in first class. So given that someone survived, that's 131 on the denominator. The probability that someone is in first class is 58 out of 131. But if I just say, what's the probability that someone's in first class, that's 176 out of 795. But if I say, what's the probability that they're in first class, given that they survived, I'm only now talking about 131 people. So that's a conditional probability. And then we can also do conditional probability the other way, which is going to give us three distributions. If we look at the row for first class, see if I can highlight this. If we look for the row of first class, what is the probability of what is the distribution of mortality? 118 died out of 176 in the first class. That's 67%. 58 survived out of the 176 in first class. That's 33%. And so on. We can do the conditional distribution of mortality if we just look at died and survived among the second class passengers. And we could look at the distribution of mortality, died and survived, just among the third class passengers. And once again, the percentages of passengers who died and survived is different when you look at first class as compared to when you look at second class as compared to when you look at third class. So again, this is suggesting that there's a relationship between class and mortality. And you could say that a person's mortality, whether or not they die or survive, depends on what class they're in. And another thing is, so for example, the probability, this number right, where is it, right here, the probability that someone survived, given that they're in first class. So among those in first class, 33% survived. And also notice that this is not the same as the other conditional probability we had right here. The probability that someone was in first class given that they survived is 44%. The probability that someone survived given that they're in first class is 33%. So those two are not the same. And in general, if you switch the order of a conditional probability statement, that makes a difference, and that changes the probability because you're changing what is given. So that's a segue to a natural conversation about independence. So if two events are independent, then knowing that one event has happened does not change the probability that the other event happens. And the way we say that as a probability statement is we say that if A and B are independent, the probability of A given B is just the probability of A. So knowing that B has happened doesn't change the probability that A has happened. There. So if two things are independent, then knowing that B has happened does not change the probability that A has happened. So the probability of A and the probability of A given B are the same. So in our particular case, in our example, the probability that someone survived, given that they're in first class, is about 33%, but the probability of just survived is 16%. So calling this A and this B, calling this A and then calling this B, that fits right into this rule here. And notice these two probabilities are not the same. And so since those are not equal, then we say that these two events, survive in first class, are not independent. It's technically correct to say that they are dependent, but usually it's best to just stick with either independent or not independent. And also, it doesn't matter which of the events you call A and which you call B. So instead of looking at first class and survived like this, I could look at first class and survived like this. The probability that someone is in first class given that they survived, we figured out earlier up here was 4427. But the probability of somebody just being in first class is 0.22. And again, this now, I guess you could say, is what we're calling A, first class, and then survived is what we're calling B. So, but still we have those two probabilities are not equal. Even though it's different than these two probabilities, it's still a legitimate check. And since those two probabilities are not equal, we say that the events first class and survived are not independent. Only if those two statements, this conditional probability and this marginal probability, only if those two are equal, this conditional probability and this marginal probability, only if those two are equal do we say the two events are independent. Somewhat related to conditional probability is joint probability, and in fact students often get the two mixed up. The probability of event A and B both happening, which is written as probability of A and B, that's referred to as a joint probability. A joint as in a place where two events come together. Often the word and, notice I've capitalized it, is done in capital letters to distinguish it from the regular use of the word and also sometimes to avoid confusion with the word and, you'll see the intersection symbol used. Anyways, in our case, let me go back to my split window. In our case, we have, if we look at the probability that someone survived and was in first class, well, out of 795 passengers, there's only 58 who both were survivors and in first class. So 58 out of 795 is about 7%. Also, I was mentioning up here when we were talking about conditional probability that the order of conditional probability makes a difference. So if you say survived given first class versus saying first class given survived, those two answers are going to be different because you're changing the information or which event is given. But for joint probability, it does not matter what order you say the two events in, because just like very similar to saying that the intersection of temple and valley is the same as the intersection of valley and temple. Those both refer to the same location. So back at my table, if I say first class, if I highlight first class, and then I also highlight survived, where those two intersect is going to be at the 58. If I say the intersection of first class and survived. But if I say survived first, and I say the intersection of survived and first class, that intersection is still happening over that number 58. So we're talking about 58 regardless of which way that's stated. So what's interesting is this discussion of joint probability and conditional probability leads us to a pretty useful formula, and that's the formula for conditional probability, which is the probability of A given B is the probability of A and B divided by the probability of B. So let's say we did not have this table to look at, and we wanted to figure out the probability that someone survived given that they were in first class, but we don't have the table to look at. But suppose we had figured out somewhere before that the probability someone is in first class is 2214. So I'm going to write that down right here. And suppose we know that the probability that someone survived and was in first class, right here, is 0.07. So if we know those two probabilities, then we can use those two probabilities in a formula. The probability that someone survived, given that they're in first class, is the probability that they survived and they're in first class divided by the probability that they're in first class. And something that I really want to emphasize talking about this that I didn't really put in the notes is that notice the event that comes after the vertical bar is always going to be the event that goes in the denominator. So over here, first class came after the vertical bar. First class is the probability that goes in the denominator. So survived and first class was the 7%, and the first class was 22%. And if you divide those two, you get 3297. You get 3297. And if I scroll up just a little bit, you will see that we had previously figured out the probability of survived given first class is 3295. But notice where that 3295 came from is this fraction. The survivors among those in first class. So given that someone is in first class, the probability that they survive, 3295. So this is getting it from the raw data, 58 people out of 176, while this is getting it from formula and dividing the right two decimals. So this is a very powerful formula in that it allows us to figure out a conditional probability given two other probabilities. And I'm not too worried about this 3295 being different from the 3297. That's just because all these probabilities are rounded off to 4 decimal places. Now, if you rearrange this formula here, let me put the split in a different place now. If you rearrange this formula here, then you get something known as the general multiplication rule. So notice in particular this version of the general multiplication rule, probability of A and B is in there, probability of B is in there, probability of A given B is in there. So the same three quantities are in there. It's just here it's expressed as a multiplication problem, like say, for example, 3 times 4 equals 12. And here it's expressed as a division problem, like say 12 divided by 3 equals 4. So even though those numbers 3, 4, and 12 are not probabilities, I'm just saying that it's the same three quantities we have here, but here expressed as a division problem, here expressed as a multiplication problem. So suppose you wanted to know the probability that someone survived and they're in first class. All you do is you multiply the probability that they're in first class times the probability that they survived, given that they're in first class. And we know both of those probabilities, so we multiply them and we get this 0.73 number, which should look very familiar for the probability of survived and first class. But you could also do this the other way around, which is why this multiplication rule is written two different ways. You could also say survived in first class is the probability of survived times the probability of first class given that you survived, which is more the first way I wrote it over here. And if you multiply, notice this is a completely separate multiplication problem from this, yet the two multiplication problems are resulting in the exact same answer. So this multiplication rule works both of these ways. Probability of A times B given A, or the probability of B times A given B. Okay, so that's the general multiplication rule, but now we're going to have a marriage of that general multiplication rule and something we talked about earlier, which is independence. So let me move this down just a little bit so you can see both of them at the same time. So here is the general multiplication rule. I'm going to highlight that really quickly in yellow, maybe. And here is a piece of the definition of independence. So notice this multiplication rule, if I knew the events were independent, sorry, let me get that just right if I can. There we go. If I knew that the events were independent, then I could say the probability of A given B, I could replace that with the probability of B. And if I replace this with the probability of B, then this would just say probability of A times probability of B. So that's what I've written here for the multiplication rule for independent events. If A and B are independent, then the probability of A and B is the probability of A times the probability of B. Just straight up multiplying those two probabilities. And you can multiply them the other way around if you wish. That's no big deal. But even though students try to do this multiplication a lot, it's very important that this multiplication will only work when the events are independent. As a matter of fact, this gives us another way of checking independence. If you multiply these two probabilities and you get this probability, then that means the two events are independent. So often I like to write this like this. Is the probability, oh, I do not have an and in here, momentito, por favor. Is the probability of survived and first class, is that the same, question mark, as the probability of survived times the probability of first class? If this multiplication works, then that means the events are independent, because that's the only time this multiplication works. So probability of survived and first class, we already know that's 0.730. The probability of survived, we know, and the probability of first class, we know. So we multiply these two, we get 0.03, and we see if it's equal to the and probability, and it's not. So because this multiplication did not work out, that's how we know that the two events are not independent. Because if they were independent, this multiplication would work out. Okay, let's look at an interesting little problem from a deck of cards. A standard deck of cards has 52 cards, of which 4 are aces. Suppose we select 2 cards at random from the deck. What is the probability of them both being aces? So I'm going to attack this in 2 ways to show that, to show 2 different ways we've learned of dealing with probability. So the first way to look at this is through the counting rule and our original formula for probability. So I want to know the probability of getting an ace followed by an ace. So the numerator of the fraction would be the number of ways to get 2 aces. The denominator of the fraction would be the number of ways to get 2 cards. So I'm going to select 2 cards at random from the deck. My denominator is the total number of ways that you can select 2 cards from the deck. But I want to know the probability of getting 2 aces. So the numerator is going to be the number of ways that I can get 2 aces. And I'm going to do both the numerator and the denominator with combinations. The number of ways that you can get 2 aces, since there's 4 aces, is 4 choose 2. Using our combination formula, that's 6. The number of ways to get 2 cards out of the deck is 52 choose 2, since there's 52 cards in the deck, and that's 1326. And if you reduce this fraction, it simplifies to 1 out of 221, or 0045. So this, for sure, is the probability of selecting 2 cards at random from the deck and having them both be aces. Now, to attack that same probability problem in a completely different way, suppose I wrote this probability like this, specifically using the word and. What is the probability that the first card is an ace and the second card is an ace? And then use my multiplication rule. So the probability that the first card is an ace and the second card is an ace is the probability of A, the first card is an ace, times the probability of B given A, the probability that the second card is an ace given that the first card is an ace. So since there's 52 cards and 4 of them are aces, the probability that the first card is an ace is pretty easy to figure out. That's 4 out of 52, which reduces to 113. And now for the second probability that I have highlighted here, given that we know the first card is an ace, that means we know there's only 51 cards in the deck. And given that we know the first card is an ace, that means there's only 3 aces left. So the probability that the second card is an ace, given that the first card is an ace, is 3 out of 51, which reduces to 1 out of 17. So if we put all that together, the probability that the first card is an ace and the second card is an ace is the probability that the first card is an ace times the probability that the second card is an ace, given that the first card is an ace, which is 1/13 times 1/17, which is 1 over 221, which is exactly the same 1 over 221 that we got here. So up here we did it by, I guess you would say, combinatorics and counting the number of ways that our event can happen, getting 2 aces, divided by the total number of things that can happen. And down here, I'm figuring out the same probability using our general multiplication rule. So that was a probability using the general multiplication rule. Now there's another rule known as the general addition rule, which is the probability of a union or an OR. Suppose you want to know the probability that one of 2 events, or possibly both events, happen. what is the probability that someone in the class is a female or an engineering major? Or you could ask, what is the probability that someone in the class is a male or a computer science major? So when I ask this problem in a live setting with the Titanic data, and I say, what's the probability that someone is in first class or survived? Automatically, students want to take this number for first class and this number for survived and add them together and divide by 795. And the problem with doing that is that it's this 58 right here that's the problem. Because this 58 is part of the total number of people in first class, but this 58 is also part of the total number of people that survived. So if you add together the people in first class and the people that survived, you're counting these 58 people twice. So the formula starts off just looking like an addition problem. Probability of A plus the probability of B. And then you have to subtract the probability of A and B, which is that little piece of 58 right there. So if you want to know the probability that someone's in first class or survived, you figure out, you add together the probability that they're in first class plus the probability they survived, and then you subtract the joint probability of first class and survived, which I misspelled. Because if you don't do that subtraction, you've counted these 58 people twice. You can also get that directly from the table. What I've shaded here or highlighted here is all the people who are in first class or survived. If you add all those together, that's 249, and 249 out of 795 is the same 3132. And if you're dealing with 3 events, it's a little bit gruesome. If you want to know the probability of A or B or C, you add those 3 probabilities together, and then you subtract all of the two-way intersections. So you subtract the probability of A and B, subtract the probability of A and C, subtract the probability of B and C, and then you have to add back the probability of all 3. It just gets really, really messy when you're trying to do formulas like that with 3 or more events. Another big topic in probability is complements. So the complement of event A, which has a bunch of different ways you can write it, but it simply consists of all of the outcomes that are not in A. And so sometimes it's called not A. So either A happens or it doesn't. And if A doesn't happen, that means the complement has. So sometimes it's the letter A with a superscript C. Sometimes it's A prime. Sometimes it's tilde A, or even bang A, like in computer science, the bang symbol for not. But the point is that either an event happens or its complement happens. So the probability of the event plus the probability of its complement have to add up to 1. And this usually comes in handy written as a subtraction problem. The probability of A is 1 minus the probability of its complement, or the probability of the complement is 1 minus the probability of A. And quite often you run into problems where they ask you to find the probability that something happens, but it actually turns out easier to find out the probability that it doesn't happen, which is the complement, and then subtract from 1.